Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we are going to discuss equations, linear equations, and systems of equations, including, of course, linear equations. So in this topic, we will discuss solutions to equations. We will differentiate between linear and nonlinear equations. We will define solution vectors and free variables. We will look at solutions to nonlinear and linear equations. We will describe systems of equations and consider a few systems of nonlinear equations. However, we will then introduce the concept of M linear equations in N unknowns. Alright, to begin, an equation is any statement that equates two mathematical expressions that have one or more independent variables or unknowns. So, for example, given three real numbers a, b, and c, the quadratic equation equates a quadratic polynomial in one variable x to 0. Given real numbers a through f, the following equation may, if a solution exists, define a conic section. Now, you can have an equation that also involves other mathematical functions, such as trigonometric, exponential, logarithmic, and/or hyperbolic functions. Consequently, all of these are acceptable equations, some in one, some in two variables. Now, some of the easiest equations to deal with involve only sums of products of the unknowns with scalars, all equated to a target scalar. So in the first case, we have 6 times x1 is equal to 15. In the second, we have a sum of two products of two unknowns, x1 and x2, each multiplied by an appropriate scalar, equaling the target scalar 24. And so on and so forth. And you can do this with an arbitrary number of variables. Such equations are called linear equations, and they are core to this course. Now, if an equation has n unknowns, then a solution to that equation are any values that these unknowns could take on that make the equality true. So, for example, given the linear equation 4x1 equals 5, there's only one solution. x1 is equal to 1.25. Given the quadratic equation we see here, it has two solutions. The first being x1 is equal to negative 2, and the second being x1 is equal to negative 0.5. The equation sine of x1 is equal to 0 has infinitely many solutions, that is, as many solutions as there are integers. So x1 is equal to n times pi, where n is any integer, is a solution to this equation. Now, in some cases, there may be many more than just a few, or even countably many solutions. For example, here is a linear equation with two unknowns. Then, by observation, we see that x1 and x2 being 0 and 2.4 respectively is one solution. However, x1 and x2 being 3 and 0 respectively is another solution. In fact, this has many more solutions. We could parameterize the solutions. So, if we let c to be a free variable, so that c can take on any real number, then letting x1 and x2 be c and 2.4 minus 0.8 times c, then this also is a solution for any real number c. Here's another example. Consider x1 squared plus x2 is equal to 0. Now, one solution is x1 and x2 equaling 0 and 0 respectively. That's one possible solution. And if c is a free variable with the constraint that c is less than 0, then both x1 and x2 being the square root of negative c and c respectively, and x1 and x2 being the negative square root of negative c and c respectively, these are both solutions to this particular equation. And these are solutions for all values of c less than 0. A few points. If there are more than one variables or unknowns in an equation, we will describe the solution as a solution vector. In general, we will choose subscripted variables, say, for example, x1 through xn. Now, we could use free variables to describe solutions, but this is going to become tedious as we will start introducing more and more of these free variables. And keeping track of them is just an extra step in bookkeeping. Instead, if a vector is referred to as a solution vector and it nevertheless continues to have variables in that solution, those variables should be assumed to be free. So, in the first vector, x1 can take on any possible values. In the second and third, we would have to be told that x2 must be restricted to being less than 0, but that would be in an annotation associated with that solution. Now, suppose we have a linear equation in three unknowns, x1 through x3. We are assuming that a1, a2, and a3 are all given as is the target right-hand side b. Now, note that we could have written this equation by bringing b to the left-hand side. However, having the target constant b on the right-hand side is standard notation, and that is the notation we will use throughout this course. Now, because there are going to be two free variables in this solution, there are actually many different possible solution vectors. One solution vector to this equation is this one, where x2 and x3 are free variables, and then we solve for x1 with respect to x2 and x3. Alternatively, we could have chosen x1 and x3 to be free variables, in which case we solved for x2 with respect to the other two free variables. The final solution is this one here, where x1 and x2 are free variables, and then we solved for x3 with respect to the two given free variables. However, interestingly enough, all three of these solution vectors give exactly the same set of points, assuming, of course, that a1, a2, and a3 are all non-zero. If a1, a2, or a3 were 0, we'd have to be a little bit more careful. But of course, if any of them were 0, it would not be a linear equation in three unknowns. Now, any equation in one or more unknowns that cannot be written as a linear equation is said to be a nonlinear equation. So, for example, all of the following are nonlinear equations. The first one has an x squared in it. The second has a product of two of the unknown variables x and y. The third has one of the variables, has the variable being the argument to the sine function. The fourth has the variable being the argument to the exponential. And in the last one, we have square of the z variable. Now, seldom, but on occasion, an equation may appear to be a nonlinear equation, but is in fact a linear equation in disguise. So in this example, you may note that if we were to multiply both sides by y, then we have a linear equation in x and y. Similarly, here, if we were to multiply both sides by x times y, once again, we would have the linear equation negative 5x plus 7y is equal to 1. Now, having a disguised linear equation is the exception and not the rule, and in this course we will always write linear equations in the standard form. Now, with one variable x, a linear equation is easy to solve. If a is non-zero, then you just divide both sides by a, and the solution is x is equal to b over a. If a and b are real, this solution is also real. With one variable, however, a nonlinear equation may be either difficult or even impossible to solve, may have any number of solutions, including 0 and infinitely many. It may have solutions that are complex as well as real. Now, for example, the quintic does not have a general solution, and there is no closed form solution of this particular quintic. This particular equation has exactly 10 solutions. Now, e to the x equaling 100 has one solution if you allow the x to be real, but it has countably many solutions if you allow x to be complex. Specifically, you will be adding multiples of 2 pi j onto the solution. However, e to the x equaling 0 has no solutions regardless as to whether or not you allow x to be real or also allow it to be complex. Now, a collection of m equations in n unknowns is described as a system of equations if any solution vector must simultaneously satisfy all of the m equations. Now, if all m equations are linear equations, we will describe it as a system of linear equations. We will often be referring to systems of m linear equations in n unknowns. Now, any system of equations that has even one nonlinear equation within it is referred to as a system of nonlinear equations. These become much more difficult to solve, and your course on numerical analysis will look at solutions to approximating solutions to such systems of nonlinear equations. For example, consider this system of two nonlinear equations. Now, let the vector u represent a solution vector, where the first entry is the value of x and the second entry is the value of y. In this case, there is a single real solution, and that is u is equal to 2, 0.5. So if x is equal to 2 and y is equal to 0.5, both of those equations are satisfied. If you allow complex solutions, there are two additional solutions, including x being 1 plus j, y being j, and x being 1 minus j and y being negative j. Now, here is another system of two nonlinear equations. So, every point in red on this graphic is a solution to the first equation, whereas every point in blue is a solution to the second equation. There is one solution that is easy to find that is a simultaneous solution to this system of two nonlinear equations, and that is the vector u equaling 1, 0. So x is equal to 1, y is equal to 0. And we see that is obviously true if we substitute those into each equation. There is a second solution, but we must use numerical techniques to even approximate it, and it's very close to our first solution, but just a little bit up and to the left. If you were to allow for complex roots as well, or complex solutions, then you would find another 4. Now, the following is a system of 3 linear equations in 3 unknowns, written in the standard form. Note that not all equations must contain all variables. In this case, the third equation does not contain the variable y. If u being the vector with values x, y, and z is the solution vector, this system of linear equations has a unique solution: 3.25, negative 1.5, 0.25. Now, this is the focus of this course. So why are we focusing initially on nonlinear equations? That's to emphasize that there are such things as nonlinear equations. They do appear in engineering, but much more seldom. And whereas it's very difficult to find solutions to systems of nonlinear equations, we will have and find and describe a very methodical, numerically stable solution for finding a solution to any system of linear equations, assuming, of course, a solution exists. Now, in general, we will have a system of m linear equations in n unknowns. The n unknowns will be represented generally by a subscripted variable, here the variables x sub 1 through x sub n. The target value for each equation is on the right-hand side of the equals sign, and here we see them as b1 through bm. Now, the coefficients of the variables in each of the equations have a double subscript. So, for example, the first subscript indicates the equation it is from. So this is a sub 3, 2 is a coefficient from the third equation, and it is the coefficient of the second unknown. So a sub 3, 2, x sub 2, the 2 representing the unknown is closest also to that unknown in the standard form. Now, we will have to refer to the individual equations, and we will do so with the abbreviations EQN1 and EQNM. However, we will of course always refer to these as equation 1 through equation m. A solution vector will be of the form x1 through xn. And so as you can see, this is going to be a vector in R to the n. Following this topic, you now understand the difference between a linear and nonlinear equation. You understand the difference between unknowns or variables and the idea of a free variable in a solution vector. You know that nonlinear equations in general are much more difficult to solve than linear equations. Usually, you're dealing with special cases. In some cases, you cannot even find a solution. You know the definition of a system of equations, and specifically a system of linear equations, and you understand the representation and the terminology we will use with a system of m linear equations in n unknowns. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!